Good morning. Well, today we're gonna talk about mathematical induction method. We're gonna talk about mathematical induction method. This will be referred to basics 44A, and of course there are basic 44B and so on and so forth. So we're gonna talk about this mathematical induction method. All right. I know there's some questions about quizzes, so we'll get to those questions later. Okay, so this week, today's lecture will be on mathematical induction method. Your questions, I know some of you have questions. Your questions will be answered. ANSW. Okay, your answer will be answered. Okay, just wait a little. Mathematical induction. What is mathematical induction? Okay, we're gonna use the first example as the first example in 44A as an example. Okay, so mathematical induction method. First of all, what is used for? It's typically used for statement, okay? Statement that's related to natural numbers. And natural numbers, we know they're 1, 2, 3, 4, 5, 6, right? These are natural numbers. For example, this statement is saying, right? The sum of the first natural number, the first n natural number, right, is, okay, so this statement is saying the sum of 1 plus 2 plus 3 plus all the way to n is a natural number, is the same as the number of natural numbers starting from 1 multiply n plus 1 divided by 2. Okay, so this is a statement. This is a statement. This is not an if statement. Okay, this is a statement. Okay, and in particular, it says, okay, what does it mean? What does it mean? Okay, here, n is a natural number. A natural number. Right? A natural number means there are 1 or 2 or 3 and so on and so forth, indefinitely, right? We know there's infinite number of natural numbers. There's no upper bound. All right, so what it means that, suppose that you add 1 plus 2, suppose we add the first 99 numbers, right? And then this formula tell us, okay, this statement, if this statement is true, and that will be starting from 1 and n is 99, so this is going to be 99 and 99 plus 1. So that's what the statement says. Okay, it means for any natural number, this is not only true for n equals to 99, it is true for any natural number n, okay? And you can have many, many cases. Okay, this is not a proof. I'm not proving this. Okay, we're not proving this. So we can trust this is basically giving us a formula, giving us a formula, okay? But the question is it true, right? So these are just examples. There are many, many such examples, right? For example, if you were adding, so this statement is saying, if I'm adding numbers, I'm going to have 237 of them. Or let's do a 365. If we're adding 1 plus 2 plus 3 all the way up to 365, what do we have? Well, in this case, it's 1 adding to 265. And this n is 265, I'm sorry, 365, and that's 365. So you can just plug in that formula, and then you will get the sum of the first 365 natural numbers. Okay, so that's what the statement says. So you can use many examples. And the question is, the first question you'll be asking, is it true? Right, is it true? And what we did here, okay, what we did above is we can verify. We can verify the left, and we can see if the left is indeed equals to right. That's called verification. So what we did here is applying the formula and verifying. So is it true? Is it true, right? That's the question. And if it is, how do you prove it is true? How do you prove that it is true? That's the question. Okay, how do you prove it, right? You can show that for n equals to 2 is true, for n equals 3 is true, for n equals to 5 is true. But can you prove that even if it is true for the first 100 natural numbers, can you still prove that for the remaining natural number, they're all true? Right, that's the question. And all what we are doing here is actually called verifying. They're not proof. They're not proof. They're not proof, right? So we need a method. Okay, so here, let me write this down, okay? Just because we could verify it is true for many cases, okay? These work can only be classified as verification, not proof. Not approved. Okay, to prove you have to say, oh, for n equals to any natural number, it is true. It is true, right? So in order to prove that, a method is developed. This method is developed, that's called mathematical induction method. Okay, so this method introduced is called mathematical induction method. And in shorthand, in short, we call it mathematical induction. Mathematical induction. Mathematical induction follows a certain format. It follows a certain format. Okay, typically. Okay, there's certain format. There's just three steps. Okay, 3 steps. Step 1, proof it is true. Okay, prove the statement is true for the smallest natural number, say sometimes it's 1. Okay, and it's not limited to 1. Okay, it's not limited to 1. It could be, 2. If the smallest, if it is true for the smallest number happen to be 2. Okay, so it's not always 1. Okay, but in this case it's 1. Okay, the step 2 is assume. Okay, assume what? The statement is true for n. Okay, assume it is true for n. And step 3 okay? Based on step 1 and step 2 to prove the statement is true for n plus 1. Okay, so these are the general steps. These are the general steps. Okay, so if we can prove all three, and what will happen? If we completed the 3 steps. If we completed the 3 steps, what does it allow us to do? What does it allow us? To reason, to rationalize, to conclude, for example, to conclude. Right? If we have proved all 3, right? If it's true for the first case and it's assume it's true for n, then we have proved that it's also true for n plus 1. And that means if for this particular case, right? If n equals 1 is true, right? If n equals 1 is true, then n equals 2 is true. If n equals 2 is true, then n equals 3 is true. If n equals 3 is true, then n equals 4 is true. You see, we get into a cycle. We get into a cycle. From the truth of one, we can derive it true forever. So allow the induction to go on forever without having to do forever cases. Does that make sense to you? Okay, so this structure allow us to conclude if it is true for 1, it is then true for 2. If it's true for 2, it's going to be true for 3. Okay, so we can keep that process going forever without having to verify infinite number of cases. Because from 1 to infinity, that is infinite number of cases. We cannot possibly do them all. So that's the logical idea behind this method. Okay, so what it allows us to complete is that it's true for n equals 1. Then it is true for n equals to 2. Okay, and then this process can go on forever. Okay, this process can go on forever. This process can go on forever. So we don't have to worry about verifying for each one of those cases. We don't have to worry about verifying for each one of those cases. Does that make sense to you guys? All right, so let's get started. Okay, so how do we demonstrate? How do we complete these 3 steps? How do we complete these steps? First of all, I want to emphasize the importance of having this proper structure, having this narrative, because this induction method is logically designed this way. Okay, so next we're going to use this structure, okay, and we're going to work on this example. Okay, we know it is a statement, right? And now what we want to prove, this is true for any natural number. For any natural number n. Okay, so we're going to follow these 3 steps. Okay, so let's write up our proof. Okay, step 1. We need to prove that it's true for n equals to 1. Okay, so for n equals to 1, right? And what do we have? The left-hand side. I want you guys to write the way I do, okay? Don't write two at the same time because you don't know if they're true until you prove it. Okay, write the way I do, okay? Don't create any other ways. If you do other ways, I'm gonna dodge the point. Okay, because you make sure this is to be proved. To be proved. Before you actually prove it, you cannot use that as truth yet. Okay, so when n equals 1, the left-hand side is equal to 1. The right-hand side is equals to that formula. So you can replace n by 1, and it is also equals to 1. Okay? And then you can say left equals to right in this case. Thus, the statement is true for n equals to 1. Okay? Some of you may say, oh, that seemed to be so obvious. Yeah. In a lot of mathematical proof, you pointed out the most obvious, but you do point it out the most obvious to make your case, okay? To make your case. In a lot of situations, yes, we do. We pointed out the most obvious to make our case. The second step, there's actually not much to it because you just make an assumption. Assume the statement is true. Assume the statement is true, then you say that is, and you need to specifically point out this specific statement. So for n, you assume it's true. There's nothing to be proved. You just add some more tools to our toolbox to complete the 3 steps. Okay. Number 3, step 3 is that we're going to prove the statement is true for n plus 1. Then you need to, I highly recommend, so right, what is that statement? What is that true statement for n plus 1? Okay, so the third step, we're going to prove the statement is true for n plus 1. So you're actually going to show what is to be proved. So that case, okay, is like this. It's n plus 1. And this is, of course, n plus 2. This is a to be proved. To be proved. Is that clear, everybody? I want you guys to understand what is you can assume. This is something you can use. It's assumed true. And the next one is to be proved. So before we proved it, we cannot use it. We cannot use it yet. Okay. So under the what we have proved in step 1 and assumed in step 2, we are going to demonstrate this statement is also true. Okay. So that is to be proved. I wish that to be clear to you. We don't know if this is true. At least we pretend. We pretend this is not true yet. Follow me? Okay. So with that understanding, we start from the left. Don't work on both sides at the same time. I cannot emphasize enough about this way of writing. You say, what a difference it makes? Because it reads differently. It reads differently. Okay. Still with all of my emphasis, when I didn't finish grading your quiz number 28, but I still see people doing that 2 sides. I don't know, I have emphasized this over and over again. If you are to prove something, you need to assume that something has not been proved yet. So you cannot assume, you cannot use it. Okay, so in this case, okay, so let's do the left. So we're going to start with this left. This is the left. Okay, this is the left-hand side. because the assumed, this is our assumed. So that we can use the assumed, okay? The assumed says 1 plus 2 plus 3 all the way up to n. These n terms is the same as that, plus n plus 1. Okay, so you can use the case 1, step 1, and you can use the assumed. But this is to be proved. This is to be proved. You cannot use it yet. Okay, and next, we're gonna work with this algebraic expression, which is of course to find common denominator, right? So we're gonna find common denominator. The common denominator obviously is 2. So we're gonna have 2 times n plus 1 over 2. With that common denominator found, we're gonna combine the numerator. We're gonna combine the numerator. So we're gonna bring these two together, right? So we're gonna have 2 times n plus 1. And of course, we're going to expand. Okay, you can see this is the rest of the step is pure algebraic, but you need to know we're going to the other side. Okay, our target. Okay, our target is to get there. We want to get there. Okay, we want to get there. Okay, by our algebraic operations, And of course, here you're going to open up the parentheses. You're going to have n squared plus n, and 2 times n times 1. So you've got 2n plus 2, right? And next, right? Next, combine these two, we have 3n, and factor. Remember, we want to get there. We factor this, what do we get? We get n plus 1 times n plus 2. So from the left, we ended up from the left, we use the assumed and whatever fact we already know to be true, and we ended up to the left, to the right. Okay, so this is the right-hand side. This equals to the right-hand side. Okay, this is the kind of way you write it. You don't work on two sides at the same time. You don't work on two sides at the same time. If you do, you're gonna lose some points because that logically is not sound. Okay, so we do care about that forms and logic structure. But anyway, without further ado, okay, so we have proved based on step 1 and step 2, we have demonstrated step 3 is true. Okay, step 3 is true. Let me make the font just a little bit smaller. Okay, step 3 is true. And then what do we say? Okay, you may like to say true for n plus 1. Just a summary. Okay, in the end, you summarize. Therefore, right? This statement is true for any natural number. Any natural number n. Okay, so this is the entirety of the proof to this statement. This statement is a formula. You actually get to use it in Calc 1, okay? And there are 2 other formula that you get to use, Okay, so let's look at number 2. Let's look at number 2. I know some of you might have questions on the most recent quiz number 30. I think I'm going to, we're just going to do the mathematical induction method, which I think we can finish today. And the rest of the time, we're going to do the, we're going to work on the, I'll work on your question, okay? If you have any. So get your question ready and put it aside. Okay, so we'll get to it. If I forget, please remind me. Okay, the second case, the second formula that you are going to use in Calc 1 is this. Okay, so 1 squared plus 2 squared plus 3 squared, as you see it, right? Plus more all the way up to n squared. And this statement, it says, right, if you, the square of the first n natural numbers, so the sum of squares of consecutive natural numbers. Okay, so I'm gonna write down the narrative. How do you express this, right? The sum of squares of the first n natural numbers. Is that narrative, does that narrative make sense to you? Does it make sense to you? Right? Excuse me. The sum of squares of the first natural numbers. This statement tells us is the same as a simple calculation divided by 6. The font's just a little bit larger. Okay, the sum of, okay, I promise you, you're gonna use that. You're gonna use this formula. In Calc 1, Chapter 5. Okay, so how do we prove it? Still the same 3 steps. Still the same 3 steps. Okay, so I'm gonna copy these 3 steps. And this time I'm asking you guys to work with me. Let's do this together. Step 1, right? You can see that mathematical induction method, it follows certain structure, a certain narrative. Okay. Now, is it first we prove the statement is true for n equals to 1, right? Is it right for n equals to 1? That's what we want to prove. Proof means that something asks you to prove, you don't know it's true yet. Then you say, hey, it is true. Yes, but you need to demonstrate. Okay? And sometimes, indeed, in mathematics, we do point it out the most obvious, even though it's so obvious. But you just want to tell the reader, hey, look, this is so obvious. Well, you probably don't want to use that word to make. You just say, this is the fact we're using and to point out to our conclusion. Okay, so the left is 1 and the right is when n equals to 1, you plug in 1 times 1, and that equals to 1 as well, right? Because it's 2 times 3, 3 times 2 is 6, 6 divided by 6 is 1. So left is Left is same as right. Okay, then you say the statement is true for n equals 1. Okay, just like as being required. Then you say, well, what if this statement is not true for n equals 1? Could that be possible? Of course. There are some cases that it's not true for n equals 1. It might start, maybe it's true for n equals to 3. So then you start with 3. In some situation that it could be true for n equals to -1. Sometimes we do expand the mathematical induction method to numbers that are other than natural numbers, even to 0, because 0 is a whole number. It's not natural. It's not a natural number, but it's, it depends, right? Depends. All right, assume the statement is true for n, which means we assume this is true. When we assume something is true, then we can use it. Okay, and you can see it's pretty similar to what we did before. And then prove the statement is true for n plus 1. So you need to modify and show the reader what is to be proved. Okay, for n plus 1, we will have another term, n plus 1 squared. On the other side, n will turn to n plus 1. So this n turn into n plus 1. Okay, so this n is also turning to n plus 1. And what does that equal to? So you can simplify the form, right? Just to combine like terms, n plus 1. So this has become n plus 2. And 2n plus 2, that becomes 2n plus 3. 2n plus 3. Okay, so this is to be proved. This is to be proved. To be proved. To be proved. To be proved, that means we don't know it's true or not. Okay, so once again, we start from left. Okay, the left is the sum of squares of the first n plus 1 natural number. But because of the assumption, we know the sum of the first n natural, the sum of squares of first n natural number is this guy, assumed. So we can apply that. And then do you see how that has been used and applied? And then we're going to find common denominator and all of that stuff, right? It's similar to what we did. And this time we want to see if you have the algebraic skill. I know you have it. Could you apply it? Could you apply it? Could you apply, right? We know the direction we're heading, right? We're going there. We want to prove this is going to be true. We're eventually going to get there. But you have to manipulate this algebraic expression so that we end up there. I'm going to give you guys a couple minutes to work on this algebraic operation. Are you ready? Try it. Okay, get a piece of paper, pencil. You guys know what to do? Get a piece of paper, pencil, get your pencil, okay? Starting from the left, and you want to end up on the right. You want to end up on the right. Okay, finding common denominators and factoring and all of that stuff. Okay, I'm going to give you a couple minutes to manipulate. Okay, I'm just going to get a cup of tea. I'll be right back. Okay, so please do it. How's it going? We know the direction we're heading, don't we? Can we get there? Okay, don't draw these curls like I do. Okay, keep your work clean. Oops. Still. But still. Okay, keep doing what you're doing. You can't help. So clumsy. Okay. How's it going? What did you get into? Anybody want to show your work? Okay. Anyway, I'm going to call you guys back. Okay. Whatever you have done, if you foil these three, it's going to take you a long time. Agree? Did some of you try that? I wouldn't go that way. Okay. I will factor out the 6 and I'll factor out the n plus 1. Okay, because you know where to go, right? We know where to go. So what you do is that you factor out these n plus 1 over 6. There's a 1 n plus 1 over 6. So what do you have left? The denominator is also factored out. So you have n times n plus 1, 2n plus 1. And then you have another n plus 1, yeah? From this one, from this side, right? You don't want it to take forever, yes? This is where the algebraic skills are needed. And then you're going to expand. So 2n squared plus, right? You have 1 times n, so 2n squared plus what? Plus what? There's 1n here plus 2n, right? And then plus 1, is that right? Did I miss something? There's a 6, I'm sorry. There's a 6 here, isn't it? 6 times n plus 1. So this is going to be 7n plus 6. Right? So I factored out the denominator 6, 1 of the n plus 1, but I still have a 6 times n plus 1 on the top. Does everybody follow me? I would also ask you guys to try to write it the way I do. To make it better organized, make it better organized instead of this form, right? You have lots of stuff, right? For example, if you write it this way, and there's a little 6 in the bottom, that's okay. But it's like somebody has a big head, a small body, isn't it? Right? You certainly can write it this way, but just try to learn another way. Just try to learn another way. Are you with me? Are you with me? Okay, so now factor the brackets. What do we get after factoring the brackets? What do we get? You should get n plus 2 times 2n plus 3, right? Well, you can verify because you know where the thing is, in proof, we know where we're going, where we should be going, right? We know where we should be going. We just have to make sure all the steps is verified, justified, correct. Yes? And that is the right-hand side. That's the right-hand side of the to be proved. You see, for the to be proved, you start from one side, you work your way up to the other side. Okay, then you also say, then you just draw a conclusion. The statement is true for n plus 1. And then we draw the conclusion. Therefore, okay, that statement, right? This statement is true for any natural number. Okay, so this is the this is number two. Do you guys want to try number 3? Number 1, 2, 3. Okay, these 3 statements, these 3 formula are actually going to be used in your calculus 1 text in that course in chapter 5. Okay, in chapter 5. Okay, so let's work on number 3. Okay. Treat this as an opportunity that you're going to improve your algebraic skill. Okay, your algebraic skill while still understanding math induction method. Okay, so the third one, I want you guys to take the lead. Okay, this is part 3. Okay, and that is equals to that. Oops. Okay, still 3 steps. Okay, still the same 3 steps. And this time I want you guys to take the lead. Right the way I recommended. Okay, right the way I did. Okay, right the way I did. Because if you do, you're guaranteed to get the points. Okay, so learn how to do that. And then you can explore other variations. But first get the first step right. Okay, so you're proving number 3. You guys have number 3 in front of you, don't you? Okay, so I'm gonna show on the screen how number 2 is done as you are working on number 3. I'm going to give you a couple minutes. I'm just going to be 1 step behind you. I think this time you guys will do better, right? You're not gonna expand by, you're not gonna expand this guy by sheer force, right? You can, but it's gonna take you a long time. Okay. You can use my hint on the screen if you want, or you can just do your own. Something is not right, working right. Did I make any mistake somewhere here? I'm checking. Oh, I made a mistake. I did. When I was using the assumption, yes. When I was using the assumption. Okay, so ignore my work. You should ignore my work. Okay, you're better off ignoring my work. Okay, that's what I use this one, of course it's not gonna work. I actually use this one to substitute, okay? You guys didn't quite follow me, did you? Or did I confuse you? Ah, my bad. You see how teacher is not always right, right? Yep. Always question your teacher, okay? Always. I knew this works. All right, are we good? Are we good? Did you guys, did some of you fall into the trap I fell into? I hope not, I hope not, right? Question the steps, question your teacher's step. I would say always, always, okay, always. That's how you learn. That's how you, don't take whatever your teacher does blindly. Of course, I made a terrible mistake. I mean, a most obvious mistake, and I found it very quickly. I do make mistakes. Your teachers do make mistakes, and you, as a student, you always question: is that right? Is that right? Right? Mathematical truth is meant to be eternity for eternity. We don't want that, mistake to be in that, to be there by mistake, right? We don't want that to be there by mistake. All right, so this one, I feel that in factoring wise, from basic algebraic perspective, it's actually easier than the previous one, right? A little bit easier than the previous one, but you got the structure, I will do the number 4 with you. I'll work with the number 4 with you guys, because number 4 represent another type of question, another type of question that can be, resolved by mathematical induction. And also is because for basic 44B, there are a lot of divisible questions. In case you guys are getting there, okay, in case some of you may want to try those problems, those questions. So I'm going to give you, show you how to prove this. okay? So is divisible by 4. What is divisible means? Of course, n is a natural number. What is divisible means? For example, 6 divided by 2 is 3. 3 is a whole number. And we say 6 is divisible by 2. Yes? For expressions, so when we say divisible by 4, that means we're saying that the remainder is 0. Okay, divisible means when you divide this quantity by 4, the remainder is 0. That's what we meant by divisible. For example, you will not say 1 is divisible by 3, right? 1 is not divisible by 3, right? 7 is not divisible by 2 because it will have a remainder, right? So divisibility is defined as such. So I'm going to give you a formal definition of divisible. Okay, divisibility. Okay, if, okay, one quantity, okay, if one quantity divided by, say, P divided by Q is equals to, let me not use a Q. Okay, sorry, I will use, I'm trying to think about different symbols. Okay, so I'm gonna use some symbols that are, for example, the number on the top is a numerator, right? It's a numerator. But the number in the bottom is called divisor, right? Divisor. And there's a quotient and there's remainder, right? So I'm just write this general form. Okay, you can use different symbols such as omega divided by a divisor equals to Q. So let's use this one instead. You can see I'm quite liberal as choosing symbols. Do you guys follow me? Okay, because symbols are just placeholders. We need to keep in mind symbols are just placeholders. It is the place they're in is important, not the symbol itself. The name of the symbol itself is not as important as the place it is in. Okay, keep in mind about that, and you're going to use it in calculus classes as well. If this is true, okay, that is, i.e., omega is equal to the divisor multiplied by the quotient. You can see the remainder is not visible, is not available. That means remainder is 0. Okay, remainder is 0. In other words, in that division, okay, the remainder is 0. The remainder is 0, Z-E-R-O. Okay. You don't say the remainder doesn't exist. That's not the right word to use. The remainder is 0. Okay, such as in the case of 6 divided by 2, 6 divided by 3, 12 divided by 3, 20 divided by 4, and so on and so forth. Okay, so these are the examples of divisibility. So whenever this happens, okay, whenever this happens, what do we say? We will say that omega is divisible by D, symbolically. So whenever you can write it this form, actually you can also say Q is divisible. I'm sorry, omega is divisible by Q, right? Yes. For example, examples, right? 6, let me write it down. 6 is equals to 2 times 3, right? And what do we say? We will say 6 is divisible by 2. But you can also say 6 is divisible by what? By 3, right? And so on and so forth. Do you guys get it? Okay. So we're going to use this concept in number 4. In number 4, of course, for natural numbers. Okay. So in this case, we're gonna prove. Okay. This guy is divisible by 4 using mathematical induction. We still have that 3 steps. Okay, so let me find that 3 steps. So you see consistency. Okay, you see consistency. 3 steps, 1, 2, 3. The first step, we have to prove it. Okay, so for n equals to 1, 5 to the power of n, when n equals to 1, it equals to 4. 4 is obviously divisible by 4, right? 4 is divisible by 4. So true, we can say the statement is true for what? For n equals to 1. Okay, assume that statement is true for n. What does that mean? Meaning that 5 to the power n is divisible by 4. But if we apply the definition of divisibility, what do we get? Okay, so then we're gonna have some other words to say. That is because we're preparing us for the next, this is preparing us for the next step. We know what the next step is about, right? That is 5 to the power of n minus 1. If it's divisible by 4, that means it is equals to 4 times a q. And q is a natural number. I don't know what it is. I don't care what it is. I just know it is a natural number. You don't have to know. We don't have to know. You follow me? That is, this is true. We're gonna use this, okay? So from this assumption, okay, from this assumed, and let's get to step number 3. So we are to prove that what is to be proved. For the case of n plus 1, this is turned to n plus 1 is divisible by 4 as well. So with 1 proved, 2 assumed, right? Step 1 proved, step 2 assumed, we are going to prove that 5 to the power n plus 1 is also divisible by 4. So let's see how we work it, okay? And from that, from what we did, okay, you can actually move this step to the next one. Okay, these are the flexible things you can do. Okay, and or you from here, right? You can say from this guy. Okay, just leave it where it is. Okay, from that we know what? We know that 5 to the power of n is equals to 4q plus 1. Okay, I'm adding 1 on both sides. Because if this is true, because we assume it is true, right? From the assumed, and we derive that 5 to the power n minus 1 equals to 4q, then we add 1 on both sides, it is still true. Okay, as a result, oops. As a result, let's see, what's as a result? We need to go back because we need to prove this guy is divisible, right? So this left-hand side is gonna be, if I split 5 to the power of n plus 1, multiply 5 to the power of n minus 1, what do I get? Five to the power of n is 4q plus 1. So I'm going to take the 4q plus 1, replace 5 to the power of n. You guys see that? And then minus 1. Did you guys see that step? Does everybody see that? Okay. So with this done, we're going to open up the parentheses. So we're going to have 20q plus 5 minus 1. Okay. And that is 20q plus 4. Yeah. I'm going to factor out the 4. I'm going to factor out the 4. And then I'm getting 5q plus 1. That is, we got this expression is equal to this other one. By definition of divisibility, what does it say? What does this expression say? This expression says 5 to the power n plus 1 is divisible by what? By what? By 4, right? Because if q is a natural number, 5 times q is a natural number. 5q plus 1 is going to be a natural number, right? So this is 4 times a natural number. So by our definition of divisibility, whenever you can write this form, you can always say omega is divisible by d. In our case, d is 4. You guys see how that definition applied? Okay. So the statement is true for what? For n plus 1. So once again, we completed the 3 steps, that journey of the 3 steps. Okay, of course, then you can say, therefore, right? Whatever the statement says, right? 5 to the power of n minus 1 is divisible by 4. For any natural NATUR number n. End of proof. End of proof. Okay, I want you guys to carefully study these structures. Okay, if you have any questions, then please bring it forward, And next we still have some time left. I wish to go over, because some of you have questions, what the student who asked the question is not here. I hope he will be watching this recording, and I'm sure he will. Okay, so come back to your question. What is your question? I think there's some question about quiz number 30, right? There's some question about quiz number 30. If you don't have any questions, please bring your questions, whether on chat or you can just turn on your audio video to ask me that questions. I'm going to bring back the let's see, what do I have here? I'm going to bring the quiz back up. I'm going to bring the quiz. Okay, I'm going to bring the quiz number 30. I don't know what the question you have there, but I do want to point out there are certain these are certain questions you might have. Okay, you might have, which I want to point it out. Okay. This week, I will make all the answers available to you, to the quizzes. And of course, next week is the final exam. Edit. No, wait, preview. So let me show you the screen here. Okay. All right. I hope these answer question number 1, you're okay, right? Question number 1, you're okay, right? Question number 2, you should be fine as well. We went over that in class. You just have to, go over those with the flow. Okay, there's a couple questions about that same graph. Question number 5, I don't expect any questions. I think it might be, the question might happen on question number 7 or 8. Okay, question number 7 or 8. For example, number 7, right? If you choose the correct answer, of course, we work this question in the class. I would not be worried about your choosing the right answer, but for E. Okay. You see, when x is positive, f of x equals 1. When x is negative, x equals -1. These are all, excuse me, these are all correct. And the domain is correct, right? But this one is wrong. You follow me? This is wrong. I don't know if that's the question, okay? If these are clear to you, then you're good. Okay, so the correct answer will be B, C, D. Oh, sorry. Not that one, sorry. B, C, D. The correct answer is B, C, D. Okay, similarly, I made up these questions because I suspect someone might be falling into that trap of the E. Okay, the next one, question number 8, is similar. We did this question in class. You can go through the steps to look it up, right? And we know that when x is larger than 2, we have certain expression. When x is less than 2, there's another certain expression. Okay, when x is not equal to 0, of course, that's not true, right? So the mistake will be here and here. Domain is correct. No, domain is not correct. Domain is a +2. Okay, x is not equal to 2. So, oh wait, the correct answer. How come I didn't give the correct answer? Oh, my bad. My bad. The correct answer is B, D, B, D, E. There's no E. Okay, so I made a mistake. I forgot, I didn't give the correct answer. The correct answer is just B and D, not including E. E is wrong. I'm sorry, Mikhail, okay? I'm glad I opened this up. I'm glad I opened it. I did make a mistake, okay? I'm going to reopen. Okay, I'm gonna reopen for you guys to get to this, and I will make the corrections. Okay, I'll make the corrections, okay? Well, I tell you the correct answer, but I still want everybody to watch the video to see it, okay? I'm very sorry, I made a mistake, okay? You don't have the correct answer choice, right? It should be the correct answer, just B and D. I will make some changes. So you're gonna have to redo the whole question, but I'll give you the time. How about that? Okay, I will give you the extension on that. And I apologize, okay? So I'm gonna make that change. Okay, so let's go back to our lecture. Any other questions you may have? Any other questions you may have? No?
In step 3 for
sorry?
In step 3 for the last one we did, why did you write 5 times 5n minus 1?
Step 3 for the last, for number 4?
Yeah.
Here?
The first like step under as a result.
As a result, yeah. Is this the one you're talking about?
Yeah.
So what's your question?
Where did we get 5 times 5n from?
I'm sorry?
Where did we get 5 times 5n from?
Because 5 times 5 to the power of n is the same as 5 to the power of n plus 1.
Oh, okay. Okay.
Right?
Yeah.
So we just split it. I see your message, Mikhail. I made a mistake. You guys just have to, I will set extension. Okay, it will become available, I mean, sometime after the class. Okay. My bad, terribly bad. So please forgive me. Any other questions? For the rest of the time, I'm going to lay out the the plan for this week and next. Okay, I'm going to lay out the okay, I'm going to lay out the plan for next week and this week. All right. Do you guys have any questions on today's lecture? So I'm going to allow 4 times on this quiz. I'll make it, I make this quiz number 13, number 30 due to tonight. Okay, tonight. Maybe I'll give a little more time. Okay, I'll give it, I'll make it due tomorrow. Let's do that. It's my mistake. My bad, I'm so sorry. All right, so it's due tomorrow night, and you get another try, you get another attempt. Okay, my bad. Okay. Let me lay out the plan for this week and next week. Okay. So this week, okay, we're going to be lecturing. So week number 15, which is this week, right? Lectures till Wednesday, which is tomorrow. Okay, you have one more quiz. And this one quiz is going to be considered point-wise is extra credit. Okay. The way I calculate the extra credit, I want you to understand is that we would have a total of 31 quizzes. So the total of quiz score. So when I calculate the total quiz score, I will have to, you know, suppose I do the total of quiz score. Quiz scores, okay? The total quiz scores. If I calculate the average of 31 quiz, I'll be divided by 31. Okay, but this number 31 is counted as extra credit. So I'm going to divide by 30. Does that make sense? Okay. Now, be aware of your grades in the grade book. Okay, it is not accurate. It's not accurate. Okay, I'm sorry to tell you that. And I'm going to explain to you why it is not accurate. Okay, so if you never missed a quiz, then your grade is closer to what it is. Your overall score is closer to what it is. However, if you missed a quiz or two, or several quizzes, whatever number of quizzes you have missed, what happened is the Canvas does not set that grade point to be 0 automatically. Do you guys understand? Suppose you missed quiz number 10, right? Quiz number 10 should be set to 0. But Canvas doesn't do that automatically. It waits for me to do it. And I haven't done that yet. Okay, so I need to go in there to set all the missed quizzes to be 0 to reflect your true grades. Okay, and the other thing is that if I divide it by 30, Canvas doesn't, there's no way I can tell Canvas to do that. I have to do that manually. So for these two reasons, and maybe other reasons, okay, other technical reasons, the quiz score or the overall score you see on Canvas is not accurate. So don't quote for it. So the final grade will have to be calculated by me. I will download all the scores and I'll follow my syllabus formula. And I will keep my promise by dividing by 30. So that's how the final grade will be calculated. Okay, so these are the two things, lecture till Wednesday. So what about Thursday this week? Right, Thursday, which is the 3rd, right? The 3rd. Is Thursday the 3rd? Yeah. We're gonna review. Okay, review, this is gonna be comprehensive. Review. Basically review for the whole semester, You can see it's gonna be very, very, it's not gonna be to the greatest detail possible, but if you have any question, I'll be happy to answer your questions. Okay, and week number 16, week number 16. This week is a final week, okay? But we will still have review sessions on Monday and Tuesday. Okay? Your final exam time starts on Wednesday, finishes Wednesday through Friday. okay? Which you're gonna do it online. You're gonna do it online, okay? So Wednesday, we will not have the official class meeting. Thursday will not be having the official class meeting, and you only have these 3 days to work on your final exam. You don't have the whole weekend, right? You guys with me? You only have these 3 days, okay? The exam will be available, say, on Wednesday, sometime on Wednesday. And you have Friday night, midnight to complete, okay? It's similar to most of your quiz format. And you have 3 attempts, so review well. This week, I will make all the past quizzes available and including their solutions, the answers available to you. So that's our plan for this week and next week. Do you have any questions? Okay, so if you haven't started review, and this is the time, okay? And I apologize for quiz number 30 that I made a mistake. So I have made the changes. I just made a little change to that question. So you can redo it. And so that's all for today. I will see you guys tomorrow, and Thursday review. Monday, Tuesday will be review, and Wednesday, Thursday, there will be no classes, and you will be working on your final exams. Okay. After all the exam are done, which is in midnight Friday, next week, I will be doing all the downloading of the grades, and so hopefully after week 16, the following week, you will have your final grades will be available the week 17, the 17th week. As long as which day, I cannot promise. It depends on how quickly I calculate the grades. Okay, so I will calculate the grades honoring my syllabus and honoring my promise that number 31 is it's extra credit. It's extra credit. Okay, so tomorrow we'll still continue our plan. Okay, we'll do whatever is to prepare ourselves for calculus classes. So anyway, without further ado, it's my office hour time. And I will see you guys on Wednesday. I'm sorry, it's not Monday today. We didn't have class on Monday. But anyway, I will see you guys tomorrow.
Thank you.
Have a great day.